Quantum computing need to be freeze nearly zero. Quantum computer are not using computer chips, but using various states of waves. These waves can vibrate in any direction and simultaneous so that they calculate more one position at same time. Think of a mouse in maze. A digital computer calculates each mouse at every joint. The power of quantum theory that you can be many places at the same time. Quantum computer freezes to nearly zero. Even a small sneeze can jeopardize the complete calculation. Our most powerful supercomputers, which is thrilling for us because we design and build quantum computers to solve precisely this type of ostensibly straightforward problem. In a world where computational power reigns paramount and technology reigns supreme, IBM is no stranger to defying expectations and stretching boundaries. The technological giant has always been a pioneer, shaping and redefining the landscape of computer science as it leads the way in technological advancements. IBM has transcended even its own elevated standards with a monumental jump that promises to revolutionize the industry. Quantum technology has arrived in the future. Imagine a computer so powerful that it can simulate novel materials to sequester carbon from our atmosphere, create low-cost fertilizers that save both energy and fossil fuels, and solve problems so complex that conventional supercomputers are unable to handle them. IBM has made this vision a reality, even though it appears to be a fantastical and audacious dream from a science fiction novel. The quantum-centric supercomputer, a magnificent example of human ingenuity, is poised to alter our conception of computing power. IBM's astonishing proposal for a 100,000 cubic cube quantum-centric supercomputer is not merely a paradigm shift. It's a seismic occurrence. It is a quantum surge into an exhilarating new era of computing capacity. We are not simply strolling into the future, we are hurtling towards it at hypersonic speeds. She holds her breath as she watches the world transform before her eyes. This machine's power is unparalleled, as it utilizes the fundamental principles of quantum mechanics to solve problems that were previously considered insurmountable. This is not merely a natural progression. This is a revolutionary shift. We are on the verge of a new era in which quantum mechanics and computer science merge to create an uncharted technological frontier. The quantum-centric supercomputer is the result of this audacious vision, which refuses to be constrained by the limitations of classical computing and challenges the very laws of physics. This system is expected to herald in a quantum-centric era of supercomputing by 2033, with the goal of addressing the world's most complex and pressing problems. It is the pinnacle of computational innovation because it combines quantum and classical capability in the same way that modern computers combine CPUs and GPUs. The 100,000 cubic quantum-centric supercomputers are a symbol of human resilience, a testament to our capacity to imagine, innovate, and overcome even the most formidable obstacles. What we are observing is more than a technological landmark. It is a monumental achievement in humanity's never-ending quest for knowledge and power. This goes beyond the realm of technology. It is about the inexhaustible capacity of the human spirit to innovate, adapt, and prevail. It is about our never-ending quest to press boundaries and explore uncharted territory in order to solve the intractable. The quantum-centric supercomputer developed by IBM is not merely a new type of machine. It is a new frontier that promises to expand the boundaries of possibility. It is the portent of a new dawn in computer science, paving the way for an era in which quantum mechanics is no longer confined to the domain of theory but forms the basis of technology for solving practical problems. Fasten your seatbelts, as the quantum revolution has begun and promises to be an exciting voyage. IBM's quantum-centric supercomputer vision is an audacious plunge into the future, a glimpse of a time when classical and quantum computing ceased to be distinct entities and merged into a computational harmony. It is a vision created of audacious aspirations, unrelenting innovation, and the unrelenting pursuit of stretching the limits of what we believe is possible. And central to this vision is the construction of a supercomputer so sophisticated and powerful that it seamlessly combines quantum and classical power. Similar to how modern computers integrate CPUs and GPUs. IBM has designated this concept as quantum-centric supercomputing. By 2033, the ultimate goal of this vision is to create a 100,000 cubic quantum-centric supercomputer that will enable humanity to confront and overcome its most pressing challenges. The quantum-century supercomputer will be unlike anything previously observed in quantum computation. Its architecture will be a feat of engineering that transcends our knowledge of computer science and tests the limits of quantum information theory. It is a new type of BA juggernaut that has emerged from the nebulous domains of speculative theory and is situated on the precipice of materialization. This vision of the future has found its first concrete manifestation in IBM's Quantum System 2, which was unveiled in late 2022. IBM intends to utilize multiple Quantum System 2s to build a formidable ensemble of thousands of qubits. This modular approach resembles the adaptability and scalability of conventional data centers, allowing for the seamless integration of multiple quantum systems. On the basis of the Quantum System 2, the vision of a 100,000 qubit cube supercomputer will be realized. To truly appreciate the significance of this vision, however, one must comprehend the inherent complication of such an endeavor. To bring about the quantum-centric supercomputer, a comprehensive reconsideration and restructuring of our approach to both quantum and classical computing is necessary. This requires advancing the frontiers of engineering, conducting extensive research in fundamental physics, and challenging the current limits of computer science and quantum information theory. Building a quantum-centric supercomputer of this magnitude is not a solitary task and requires a collaborative effort involving the most brilliant minds in the field. This understanding prompted IBM to form partnerships with the world's foremost academic institutions and research organizations. The University of Tokyo and the University of Chicago, whose contributions to quantum computer science, quantum components, quantum algorithm design, and quantum communication have been recognized, have become the first partners in this endeavor. They are collaborating to make 2033 the year of quantum-centered supercomputing. In addition to being a tremendous surge in technological advancement, this vision represents a paradigm transformation. It underscores the expanding realization that classical and quantum computation are not antagonistic, but rather too difficult for the same whole. Each has distinct advantages, and the true power of computation rests in leveraging these advantages within a unified, integrated framework. This innovative viewpoint serves as the foundation for the quantum-centric supercomputer vision. In essence, the vision aims not only to construct the most powerful computer ever created, but also to fundamentally alter our conception of computation. It is about revising the game's rules and challenging our collective imaginations to envision a future that is as inspiring as it is awe-inspiring. IBM's vision of quantum-centric supercomputing transcends traditional computational paradigms, ushering in an era in which quantum and classical computing coexist and seamlessly collaborate. Of the most vital elements propelling this vision at the pioneering Heron processes and quantum system. The Heron processes are emblematic of the advancements achieved in classical computing power strides. They represent IBM's cutting-edge classical processor technology designed to facilitate the complex procedures of quantum computing, such as complex control algorithms and error correction protocol. Heron is not merely another classical process. Rather, it is a crucial instrument calibrated to a business and designed to complement the quantum voyage. In contrast to classical computing, quantum computing deals with quantum bits or qubits, which can simultaneously exist in multiple states due to the peculiar properties of quantum mechanics. This concept, known as superposition, in conjunction with quantum entanglement, provides quantum computers with unrivaled computing capacity. Managing and exploiting this power, however, requires a level of control that traditional computers struggle to provide. This is where Heron mechanisms enter the picture. The Heron processor is designed to function in the demanding environment of quantum computing, which is characterized by extremely low temperatures and rapid computations. Represents the symbiosis of classical and quantum computing and serves as the vital link between these two disparate domains. And while the Heron processes form the classical backbone of the Quantum System 2, which is the quantum core of IBM's ambitious vision unveiled in late 2022, the quantum system is the quantum heart of IBM's vision. Is an engineering marvel that incorporates 1,000 qubits, making it the only quantum entity in the extant environment. Based on the design of Quantum System 1, Quantum System 2 offers substantially enhanced quantum volume, a vital performance metric for quantum computers. The robust design of Quantum System 2 enables it to operate within larger quantum networks while minimizing qubit error rates and increasing qubit coherent times. The integration of the quantum system's two inherent processes is nothing short of revolutionary, resulting in an architecture that transcends the classical quantum dualism. This integrated system, the quantum-centric supercomputer, will utilize the classical processing prowess of Heron processes to efficiently administer the Quantum System 2's quantum capabilities. Both Heron and Quantum System 2 serve as the prototype for the envisioned 100,000 qubit quantum-centric supercomputer. They represent an intricate ballet between the classical and quantum worlds, demonstrating the power that can be channeled when these two distinct realms collaborate. However, in this quantum revolution where quantum and classical computation have united forces, a germane query arises. How do quantum computers compare to today's robust classical supercomputers? This question is persuasively answered by IBM Quantum and UC Berkeley's Quantum Utility Experiment, which foretells a future in which quantum computing triumphs. The experiment began with nerves running high and cautious optimism, simulating the quantum bearment on some of the most powerful supercomputers in the United States, including the Lawrence Berkeley National Laboratory and the National Energy Research Scientific Computing Center. The team sought to determine whether their quantum processor could produce reliable results, rather than viewing this as a competition. And by utilizing some of IBM's innovative error mitigation techniques, all expectations have been met. Surprisingly, the quantum device not only matched the precise classical outcomes, but also outperformed the approximate classical outcomes when the exact answer was available. Even as the team moved to circuits inaccessible to classical methods, the quantum device continued to perform with unmatched dependability. Therefore, on the one hand, IBM has made significant progress on the issue of scale, while on the other, coping with noise, an entirely distinct problem, necessitated a novel strategy. Quantum computers are notoriously susceptible to noise disturbances that lead to inaccuracies in computation. IBM, however, has developed error mitigation methods that effectively mitigate the effects of noise on quantum computations through years of persistent effort. This advance was only possible due to the construction of a quantum system of unprecedented reliability and size. This quantum utility is a cuboid device with high coherence types, and what is intriguing about it is the demonstration of quantum computing's prowess. The outcome of the experiment comparing the precision of classical supercomputers to quantum 1 supercomputers was found to be noise. Surprisingly, the error correction techniques employed by the quantum computer enabled it to match or even surpass the precision of classical supercomputers. IBM recognizes the need to join forces with the world's top academic institutions and research organizations in order to build the Quantum Center supercomputer. The initial steps on this path have led to partnerships with the University of Chicago and the University of Tokyo. Both of these institutions are renowned for their innovative research and advancements in the field of quantum computing, including the design of quantum components, quantum algorithm development and quantum communication. These partnerships seek to accelerate the development and execution of the quantum-centric supercomputer by combining their unique knowledge, skills, and resources. It is anticipated that the expertise from the University of Tokyo and the University of Chicago will expedite the realization of IBM's ambitious 100,000 qubit vision by addressing the myriad of complex technical challenges that arise. The University of Tokyo's cutting-edge research in quantum mechanics can aid in the improvement of quantum components and quantum communication technologies. Similarly, the robust computer science program at the University of Chicago can aid in the design and optimization of quantum algorithms and quantum information theory. The character reflects the realization that the world's most pressing problems require global solutions. In addition, it represents a concerted effort to utilize refined scientific knowledge for the benefit of humanity. The path to making 2033 the year of quantum-centric supercomputing necessitates not only innovation, but also collaboration, and these partnerships exemplify just that, constituting a significant step towards a thrilling quantum future. Thanks for watching. Please do hit the like and subscribe button.